Welcome to solverfy.
For this question with multiple parts, we'll start with the general expression for the ionization energy of any one electron species. As mentioned in the chapter and in a previous problem, the energy is going to be equal to the constant 2.18 times 10 to the negative 18 multiplied by the charge of the ion squared, the positive charge, divided by the energy level in which the electron is found before removal. It's then minus 1 over infinity, but 1 over infinity is 0, so we don't need to include 0 in our denominator. We'll then multiply that by Avogadro's number, because this will be the energy for just one electron, to determine the energy for the removal of a mole of electrons. We multiply by Avogadro's number. So to determine the ionization energy for B4+, it'll be 2.18 times 10 to the negative 18 joules multiplied by boron has a charge in its nucleus of 5, so it'll be 5 squared. Don't let the 4 plus confuse you. There's still one electron. That's why the charge on the cation is 4 plus, but the actual charge on the nucleus is 5 plus. We divide that by the location of the last electron, which will be in the lowest energy state, energy level 1, and multiply it by Avogadro's number, and we get 3.28 times 10 to the 7 joules per mole. Now to calculate the wavelength associated with the removal of an electron from helium plus in energy level 3, we'll use the same equation up here. Because it's helium, Z is 2, and because we're removing it from energy level 3, then N is 3. This will give us the energy. We ultimately need the wavelength, but we need to get the energy first. We get 9.69 times 10 to the negative 19 joules. Wavelength can then be calculated from a previous equation that was rearranged, where energy is equal to Planck's constant multiplied by the speed of light divided by the wavelength, or wavelength is equal to Planck's constant multiplied by the speed of light divided by the energy. And we get a wavelength of 2.05 times 10 to the negative 7 meters. Multiply that by 1 times 10 to the positive 9 to convert the meters into nanometers, and we get 205 nanometers. And for the next one, we're now removing an electron from B3+. Beryllium has 4 protons, so it has a charge of 4, and that's Z. N is, we're removing it from energy level 2, so N is 2. So we'll use the same equation as we've been using all along, 2.18 times 10 to the negative 18 multiplied by the charge of the nucleus, 4 squared, divided by the energy level from which we're removing the electron, 2 squared, and we get 8.72 times 10 to the negative 18 joules. So the wavelength will then be equal to Planck's constant multiplied by the speed of light divided by the energy that we just calculated at 8.72 times 10 to the negative 18. We then get a wavelength of 2.28 times 10 to the negative 8 meters. If we multiply that by 1 times 10 to the 9, positive 9, we'll convert the meters into nanometers, and we get 22.8 nanometers.